Binary log loss, also known as binary cross entropy. Binary log loss scores probability forecasts for yes or no outcomes. It asks, how much probability did we assign to what happened? The truth is either 1 or 0. We forecast one number, Q, the probability the event happens. The other outcome gets 1 minus Q. The scoring rule only sees the outcome and the forecast. Start with one observation. If the event happens, the forecast is judged by Q. If it does not happen, the forecast is judged by 1 minus Q. In both cases, we use the probability assigned to the truth. The compact expression is the switch. When the outcome is 1, it keeps Q and removes 1 minus Q. When the outcome is 0, it removes Q and keeps 1 minus Q. One formula now covers both outcomes. Now turn assigned probability into a penalty. Larger probability on the truth should be better, but a loss should be smaller. So we use negative log. High truth probability gives small loss. Low truth probability gives large loss.
This curve shows the shape of the penalty. Near the correct side, loss is close to 0. Near the wrong side, loss rises sharply. Next, we read 3 points on the curve for outcome 1.
For a true outcome of 1, Q equals 0.99 puts 99% on the truth. The negative log loss is about 0.01, almost no penalty. A 50-50 forecast is not a disaster, but it is not very informative. The truth received probability 1/2. The negative log loss is about 0.693. If the event happens but Q is 0.01, the truth gets 1%. The negative log loss is about 4.605. Tiny probability means a large penalty.
With many observations, each row has its own outcome, y sub I, and forecast, q sub I. For that row, call the probability assigned to what happened a sub I. If rows are independent, multiplying the a sub I values gives the likelihood of the observed outcomes. The product is awkward because it multiplies many small numbers. So name each row probability a sub I. The likelihood is the product of those row probabilities. Taking log turns a product into a sum. Then, each log of a sub I expands into the two outcome terms on screen.
The log likelihood is still a score, where bigger is better. To make a loss, multiply by -1. Then average over rows. This is binary cross entropy, or BCE. It is also called binary log loss. At the row level, the rule is simple. Look at what happened. Take the probability assigned to that outcome. Apply negative log. Then average these row losses over the data set. Now move from a sample to the population. Suppose the true chance of the event is P, but our forecast is Q. In expectation, the event occurs with probability P and does not occur with probability 1 minus P. If the event happens, the loss is negative log of Q, weighted by probability P. If it does not happen, the loss is negative log of 1 minus Q, weighted by 1 minus P. The expected loss is the average of those two cases. To find the best forecast Q, differentiate the expected loss. The derivative has two parts, negative P divided by Q plus 1 minus P divided by 1 minus Q. Put them over a common denominator and the numerator simplifies to Q minus P. Inside the interval from 0 to 1, Q times 1 minus Q is positive. The derivative is 0 exactly when Q minus P is 0. That gives Q equals P. The second derivative is positive, so this point is a minimum. The graph shows the result visually. When the true event probability is 0.7, expected loss is lowest at Q equals 0.7. Forecasting too low or too high increases the expected loss. In finite data, the observed event rate plays the role of the population probability. For the interior case, with one shared forecast Q for every row, the loss is minimized when Q equals the fraction of observed ones. Boundary cases sit at the edge. That is the derivation. One row gives the probability assigned to the truth. Many rows give a product. The logarithm turns the product into a sum. The negative average is binary cross entropy. In expectation, the loss is minimized when Q equals the true probability. If this helped, hit like, subscribe for clear machine learning explainers, and share it with someone learning binary cross entropy. I will see you in the next one.